rectifier. So first of all, what is rectifier? Rectifier is a device that converts a alternating current to DC current. Now this is not the form of DC which is required for the applications like mobile phone, like LED television. So this type of DC is not pure DC, this is known as a pulsating DC. So throughout the analysis of the rectifier, initially we assume that the diodes are ideal, or basically we are following the ideal model. So this basically by applying this particular approach, the complexity, the mathematical calculation may be reduced. The application of rectifiers, these applications are in the DC power supply, mainly in the mobile phone chargers, LED television charger. Now we have the types of rectifiers. Basically rectifiers are classified as the half wave and the full wave depending upon the output. So the full wave rectifiers are classified as the center type rectifier, where we utilize only 2 diodes, and in the second one is a bridge rectifier where we utilize 4 diodes. So first is the half wave rectifier. So in the half wave rectifier, it is defined as a circuit that only allows the half portion of the waveform, half portion of the input waveform, or basically it converts a bidirectional current into a unidirectional. So we have the circuit where we utilize a diode by assuming that initially the diode is ideal. We have the load resistance and we are measuring the output across the load resistance, and at the input side we are applying a sinusoidal type of waveform which is having a peak value Vm, and the time period of this waveform is capital T. The equation for the input signal is given as Vi equals to Vm sine omega t, where omega is the frequency. Now what happens when we are applying this particular input signal to the circuit? During the positive half cycle, means when input is greater than 0, when we are applying some positive potential at the P side of the PN junction diode, so it will allow current to flow, and we can say that the diode starts conducting. So we have considered now both the cases. First case when we are applying the positive half cycle, and the second case when we are applying a negative half cycle. So during the first positive half cycle, as the diode is ideal, so it can be replaced by its short circuit equivalent. So once it is short circuit, the current will flow in a clockwise direction and the output voltage will be nothing but equals to the input voltage. Means whatever we have applied the input, the same will be the output. Means we are getting a positive peak similar to the input signal. Now what happened during the negative half cycle? When the negative half cycle, the current will flow in opposite direction. Now as the current will flow from N to P, so what happened? Diode will not conduct, because diode will not allow current to flow in opposite direction. As a result, the diode will be treated as open circuit. So once the diode is open circuit, no current will flow through the resistance R, and we can say that the output, which is across the load resistance R, will be 0. So what happened? This circuit has basically rectified the positive peak, whereas the negative peak, the output will be 0. So this is the output waveform corresponding to the half wave rectifier. We can see here that only the positive peak of the input signal is rectified, whereas during the negative peak the output is 0. I have also marked the DC voltage level corresponding to this. These values will be calculating in our next slides. So there are some parameters associated with the rectifiers. So the name of these parameters are the RMS voltage, average voltage, or DC voltage. Next we have the ripple factor, we have the efficiency, and lastly we have the PIV rating of the diode. PIV stands for peak inverse voltage. So first of all, how we are calculating the RMS? So for any waveform, we can calculate the RMS. RMS stands for root mean square. So root mean square means if we have the input waveform, let's say the time period is 0 to t and t here will be, let's say, 2 pi. So the RMS voltage Vrms can be given as under root, which is root mean square. So we can say that this result, this formula will give you the RMS value associated with the half wave waveform. So here we can say that the output is also similar, the waveform is very similar with that of the input. So during the first cycle, positive half cycle, we have the output. So this will be 0, pi and 2 pi. So the time period is basically 2 pi, and what happened, the maximum value of this waveform was Vm. So we have Vm sine omega t square. So we are getting Vm square sine square omega t d omega t, with the limits are from 0 to pi, because the signal exists from, the output signal exists for 0 to pi values only. So by integrating this and by solving this, we are getting a result that the RMS voltage for a half wave rectifier is given as Vm by 2. So this is very important result. This will help us in calculating the ripple factor and the efficiency associated with the half wave rectifier. Next parameter here is the average voltage. So average, we can basically calculate the area under the curve of the output waveform. It will give us the average voltage. So V average, we have a general relationship for average 1 by t and 0 to t xt dt. It will give you the area under the curve of the waveform. So here we can see that the time period was 2 pi and the signal exists for only 0 to pi. So as on integrating this over the limit pi, we are getting a result which is Vm by pi. Means we have calculated two important parameters associated with the half wave rectifier. First is the RMS voltage, which is Vm by 2, and the second one is the DC voltage, or which is also referred as average voltage, and the formula is Vm by pi, where Vm is the peak value of the output waveform. Now we have the ripple factor. Now what happens, since we are getting a DC superimposed on the AC component, so as a result there are some ripples present in the output waveform, which shows it is a which is known as a ripple factor. So generally we will calculate ripple factor as it's a ratio of the AC voltage to the DC voltage. Also we are aware that VAC equals to VAC square equals to VDC square minus of Vrms square. So by utilizing this, we are getting a result that will represent this as gamma equals to under root of Vrms by Vdc square minus 1. So by putting the values of Vrms and Vdc, Vrms we are putting which is Vm by 2, and the value of Vdc we are putting which is Vm by pi. By substituting these values, we are getting the ripple factor for a half wave is 1.21. Again, this is a very important result. We will compare the result of ripple factor of half wave and later on with the full wave rectifiers. Next is the efficiency. So the efficiency is basically defined as a ratio of the DC output power to the input AC power. So what happened in the circuit, in the half wave circuit, we are having a resistance, load resistance, and let's say RF, small rf is a forward resistance of the diode. Initially what we assume that the diode is ideal, so RF is 0, But for a practical diode, we assume that there is some finite resistance which will affect, which will be there in the calculation of the efficiency. So the AC power can be given as I RMS square multiplied by the total resistance. So the total resistance, if we view from this side, we are getting small rf plus capital RL. Now the DC power is only associated with the load, which is RL. So we are getting PDC equals to IDC square multiplied by RL. Now IDC we have already calculated. IDC is also known as average value. So average value was Im by pi. If we will substitute in this equation, let's say equation number 1, and by applying a small assumption that generally the load resistance is of the order of kilo ohm and this forward resistance of the diode is very small. It's very small. So what we can assume here that if RL is very high in comparison with RL, then we are getting efficiency which is around 40.6%. Means it shows that only 40.6% of the power is converted to DC. So this efficiency is very less. So we are moving towards the PIV. PIV stands for peak inverse voltage, or it is also referred as PRV, peak reverse voltage. So it is the maximum reverse bias voltage applied to a PN junction diode before it enters into the Zener region. So basically we are calculating the PIV, the peak inverse voltage, when the diode is in reverse bias condition. So as we are aware that in a half wave circuit, under the negative half cycle, the diode will be open circuit, and whatever is the voltage across this open circuited diode will be known as the PIV. So from this circuit we can see that the current in the resistance R, in the load resistance R, will be 0, and we are getting V output is PIV equals to only Vm. Again, this is also an important result. Now we have a small numerical here corresponding to the half wave rectifier. A crystal diode having an internal resistance of 20 ohm. Although we initially assume that the diode is ideal, that means the forward resistance is very small, nearly equal to 0, but in numerical, let's say we are considering the resistance is of the order of 20 ohm, is used for half wave rectifier. So we can draw the circuit first, that we have a diode and whose resistance RF is nothing but 20 ohms. We have a load resistance of RL which is 800 ohms, and here we are applying the input signal. So if the applied voltage V, the input signal V, which is 50 sin omega t, and the load resistance is 800 ohm, find the value of Im, where Im is known as a peak value or the maximum value. Next, IDC, DC, or we call it as this is the average value, IRMS, which is the root mean square value, and next is the AC power input and the DC power input. Also we will be calculating the efficiency. What is the rectification efficiency for a half wave circuit? We are already aware that when the diode is ideal, the efficiency is nearly 40.6%. So how we can solve this? We have the input signal Vin equals to 50 sin omega t. That means we have a maximum value of input signal which is equal to 50 volt. So if the input is 50 volt, so we can calculate the value of current. What is the maximum value of current? How can we calculate? Im will be Vm divided by Rf plus capital R, because when the diode is on, then only we will be able to calculate the maximum value of current, and it is nothing but Vm by R plus R. We are considering both the resistances, means the input impedance of the resistance, input impedance of the diode, also the load resistance. So here we can clearly see that we have the Vm which is 50 volt, we have the forward resistance of the diode which is quite small, 20, we have the load resistance which is 800, So we are getting a current of 61 milliampere. This is called as a maximum or the peak current. Now with the help of this peak current, as we are already aware that the average or the DC current is given as Im by pi and the RMS current is given by Im by 2. So with the help of these two relationships, we can calculate IDC and IRMS. So IDC is 19.4 whereas IRMS is 30.5 milliamperes. Now next is the AC power input. How can we calculate the AC power input? We have already seen that AC power input will be nothing but I square R, where the I is IRMS square and the total resistance is RF plus RL. RF is the internal resistance and RL is the load resistance. So here we can compute the output, AC output power, which comes out to be 0.763 watts. Similarly, if we are having a IDC, then we can calculate the DC power. So DC power is again I square R, but as we are already aware that output side we have a resistance which is RL only, so we are getting IDC square multiplied by RL. So by calculation this result will be around 0.301 watt. So here we can calculate the efficiency. Now efficiency we are already aware, it is a ratio of DC output power to the input AC power, and if we want to calculate the percentage efficiency, we need to multiply by 100. So we can see that ideally we have observed that the efficiency was 40.6, whereas practically when we have considered the internal resistance of the diode, the efficiency comes out to be around 39.5, which is quite less, which is less than the ideal case. So since the efficiency is very less, so we are moving towards the other rectifier which is known as full wave rectifier. So in the full wave rectifier, when the circuit is able to transform both positive as well as negative half cycle of the input waveform, then the circuit is known as full wave rectifier. So the full wave rectifiers can be further classified as the full wave bridge rectifiers and the center tap full wave rectifiers. We will see what are these circuits. After that we will see what is the RMS, average, ripple factor, efficiency and the PIV associated with the full wave rectifiers. So we have the circuit here, bridge rectifier. In the bridge rectifier we require 4 diodes, and again our assumption was followed that the diodes are ideal. Initially the diodes are ideal, means during the forward bias condition these diodes will be replaced as short circuit, whereas under the reverse bias condition the diode will be treated as open circuit. So first of all we will consider the positive half cycle. So when we are considering the positive half cycle, what we can observe that diode D2 and what happened diode D3, they are on because the current will flow in this particular manner, whereas diode D1 and diode D4 is off because the current will not, this diode will not allow current to flow. So we have drawn the equivalent circuit here, and if we will apply KVL in this particular loop, we can observe that V output equals to V input, means whatever the input signal we are applying, the same kind of signal we are getting at the output side. So we will draw the signal. Now we are considering the negative half cycle. So in the negative half cycle we can see that the current will flow in an opposite direction like this. So what we can say that diode D4 and diode D1 is on, they starts conducting, whereas diode D2 and diode D3 they are off. Off means they will be represented by open circuit, whereas the other two diodes are represented as short circuit because we assume that the diode is ideal. So here again the output is nothing but Vm. So we can observe that when we are applying positive peak, we are getting the output which is also peak value is Vm, and when we are giving a negative half cycle, then also we are getting a waveform which is in upward direction. That means this circuit has rectified both both positive and negative cycles, and it will result in a waveform which is like this, having a peak value of Vm, and the time period we have defined as T. So this is the output waveform for a full wave rectifier. Now we will see the other type of full wave rectifier, which is known as center tap. So the center tap full wave rectifier utilizes only two diodes. But it requires a special type of transformer which is known as center tap transformer. So basically what happened in the center tap transformer, the secondary side got split up into two parts. So whenever we are applying input voltage at this particular end, the same voltage will be induced at the secondary side. So again we will see, let's say if we are giving the positive half cycle, so what happened when we are giving a positive half cycle, the current will start flow like this, and what happened, the diode D1 will be turned on, diode D1 starts conducting, whereas when the current is flowing in this particular direction, the diode D2 will basically, it will act as open circuit because the diode D2 will not allow current to flow. So we have both the cases now, positive half cycle as well as negative half cycle. So as we are applying the positive half cycle, we are getting an output which is same as that of the input signal, and when we are applying a negative half cycle, the diode D1 is open circuit and the diode D2 is short circuit, and again we can calculate what is the value of V0. So the V0 is, the peak value of the V0 is Vm. So as a whole, if we combine both the peaks, positive and the negative peak, then the resulting waveform will look like this one, having a peak value of Vm. So this is a working for the center tap full wave rectifier. Now we will calculate the RMS voltage. So as we have already seen that for a full wave output waveform, let's say this is from 0 to 2 pi, and here we have, let's say V0, peak value is Vm. So we can say that the time period of this particular waveform for the output waveform is now changed from 2 pi to pi. That's why we have pi over here, and we are also integrating over the limit which is 0 to pi. So if we'll solve this, so we're getting a result for the RMS voltage of the full wave rectifier, which is Vm by root 2. As we have previously studied that the RMS for half wave rectifier is Vm by 2. Now we will calculate the average voltage. So again we have seen that how we can calculate the average voltage for a waveform. We just need to calculate the area under the curve. So the area under the curve for this particular waveform can be obtained. We need to calculate this particular area 0 to pi. So here we can write down that the time period is pi, because the signal, this particular waveform, repeats after pi interval. So if we'll solve this, we are getting a result that VDC, or the average value for a full wave rectifier, is 2 Vm by pi. Naturally, for the half wave we have seen a single peak, but for a full wave rectifier we have seen two peaks. So definitely the average value or the DC value get doubles. So if we'll solve this, we are getting a result that VDC equals to 0.636. Now we have the ripple factor. As we have already calculated that the ripple factor is a ratio of the AC voltage to the DC voltage. So we have already derived a small relationship that ripple factor can also be calculated with the help of RMS voltage and DC voltage, which is given as under root of Vrms by Vdc whole square minus 1. So for a full wave rectifier, we just substitute these values and we are getting a ripple factor of 0.48. Means if we compare the result of half wave, we are getting a ripple factor of 1.21. For full wave we are getting a ripple factor of 0.48. Means more ripple factor, it shows that there are more ripples present in the output waveform. So we can say that the full wave rectifier is having a less number of ripples as compared to the half wave rectifier. Now the important parameter here is efficiency, because we have seen that for a half wave rectifier the efficiency was very poor, around 40.6%. So here again we are following the similar steps. And by making a small substitution, that if the load resistance is very high in comparison with the forward resistance of the diode, then the efficiency can be calculated as 81.2, which is double as compared to the 40.6% for the half wave. So we improved the efficiency. We are getting efficiency which is double that of a full wave for that of half wave rectifier. Now the PIV, again we will see the PIV calculation for both bridge type circuit and for the center type rectifier. So we can see here that when during the positive half cycle, initially this diode was open circuit and this diode was open circuit. So PIV, it is a maximum voltage applied to a PN junction diode before it enters into the Zener region. We'll be using this. So we'll be calculating PIV when the diode is off. So we'll apply KVL either in this direction or in this outer loop. We are getting a result that PIV equals to only Vm. Now we'll calculate the PIV rating for the center type full wave rectifier. So we have seen that during the negative half cycle diode D1 was off, and what happened, we'll apply KVL in this particular loop. We are getting an equation that PIV equals to the secondary voltage plus VR. We have calculated the value of VR nothing but Vm, and whatever the input we have applied, the peak value is Vm. So the PIV rating for the center type full wave rectifier is nothing but that is double, which is 2 times of Vm. So we have presented now the comparison between the half wave rectifier and the full wave rectifier. So we can see here that in the half wave rectifier we require only the one diode, whereas in full wave rectifier we have 2 diodes or 4 diodes depending upon the configuration. If the configuration is a center type, we require only 2, whereas if in a bridge circuit we require 4 diodes. The maximum efficiency we achieved in the full wave rectification case is 40.6, whereas for the full wave rectifier we have calculated the efficiency which is around 81.2%. Now the ripple factor, as we have seen that ripple factor is high for half wave rectifier, which is 1.21, that shows that more ripples are present in the output waveform of a half wave rectifier, whereas less number of ripples are present in the output waveform of a full wave rectifier. Now the voltage regulation is good, but here the voltage regulation is better as compared to the half wave rectifier. We have also calculated the PIV values. So PIV rating for the half wave rectifier we have calculated as Vm, whereas for bridge and center type we have calculated as Vm and 2Vm respectively. Also we can write down the average voltage root mean values in the comparison chart. So we can write down here that the average voltage is Vm by pi, whereas for full wave it is 2Vm by pi. Also the root mean square voltage for a half wave is Vm by 2, whereas for the full wave rectifier it is Vm by root 2. So this is a small comparison for the rectifiers. We have not used any filter circuit, means any RC filter or the capacitive filter at the output side. We can consider the capacitors also. So we have another question here. We have the 4 diodes which are in a bridge rectifier configuration, and it is considered that the forward resistance of the diode is 1 ohm and it is having a infinite resistance, as we are already aware that diode offers a very huge amount of resistance when it is working in a reverse bias condition. The alternating current, which is 240 volt RMS, is applied at the input of the bridge circuit. The load resistance here is the 480 ohms, So we need to calculate the average value of the load current and the power dissipation in each diode. So let me draw the bridge circuit first, because then only we'll be able to see that what all resistances are into the picture. So as we can see here that the resistance, if we denote the resistance of the diode as small rf, and it is given as 1 ohm. So during the positive half cycle, what happened? Diode D2 and diode D3 are on, whereas diode D1 and D4 are off. So when diode D2 and diode D3 is on, that means we are getting a resistance which is RF for diode D2 and RF resistance for D3. Means in the forward bias, in the positive half cycle, we are getting the resistance which is 2 times of RF, and the resistance here is, let's say, the load resistance RL, which is given as 480 ohms. So during the calculation time, we will see that the overall resistance will be 2 times of small RL and RF and the load resistance capital RL. So first we will see what is the peak value of the voltage, as we are aware that we have applied a alternating supply of 240 RMS. So first, with the help of this, we will calculate what is the maximum value. So maximum value can be obtained by multiplying this by a factor of √2. Now we can see at any instance in the bridge circuit, the effective resistance, as we have seen that the effective resistance is nothing but 2 times of RF plus RL. If we will visualize effective resistance from this side, we can consider both the cases, negative cycle and the positive half cycle. We are getting a same amount of resistance, which is 2 times of RF plus RL. So the maximum current can be obtained by Im equals to the maximum voltage divided by the effective resistance, which is Vm divided by 2 times of RF plus RL. So we are getting a result which is 0.7 ampere. Now the DC value of mean value, DC value or the average value, all are the same things. So as we are already aware that we are given a bridge rectifier circuit, which is a full wave rectifier. So for full wave rectifier, the calculation is 2 Im by pi. The DC voltage can be given as 2 Im by pi. So we can calculate here, the value is 0.45 ampere. Now we are calculating the RMS. So RMS, since each diode conducts only half a cycle, so the diode RMS current is, we are not calculating the overall RMS current. The RMS current here is Im by 2. So it will give you a value 0.35 ampere. The power dissipation in each diode is nothing but I square multiplied by the resistance of the diode. We have seen that the resistance, forward resistance of the diode is nothing but 1 ohm. So if we multiply I RMS square multiply by RF, will give you the power dissipation in the each diode, which is around 0.123 watt. Now we'll consider another example. We have to determine the output waveform for the network, and we need to calculate the DC level. So here we have utilized, the circuit is in bridge configuration, but we have only 2 diodes, and we have these resistances, the load resistances, which is the value of 2K, and other 2 resistances which is also having the same value. We just select these resistances because we'll use these resistances, we can minimize the calculation here. So we have applied a signal, input signal having a peak value which is 10 volt. So how can we determine the output waveform? First we will consider during the positive half cycle. So what happened during the positive half cycle? Diode D2 is on, whereas diode D1 is off. So when diode D2 is on, we have this equivalent circuit, it will be represented by short circuit because we are considering the ideal approximation, and here the diode is open circuit. So if we simplify the circuit, we observe that these two resistances 2K and 2K, they are in series. So if we have applied a peak value of 10 volt at the input side, so the voltage will be divided and the output voltage will be calculated as V in multiplied by the resistance R divided by R plus R. So which is nothing but input is 10 multiplied by 2, which is 2 plus 2, right? So we are getting here which is a 5 volt. So this input is given as 10 volt, but we are getting a waveform at the output side which is of 5 volt now. Now during the negative half cycle, we observe that here the diode is open circuit and here the diode is short circuit. So the current will flow something like this. It will go in these two branches, current get divided, and if we'll solve this, now again it appears that both the resistances are in series now. So if 10 volt is applied at the input side and if two resistances are in series, as we have already seen that the voltage get divided here, and we can easily calculate that the voltage across the second resistance now is 5 volt. V output equals to 5 volt. So what we observe here, that although we have basically use two circuits, but we observed a waveform that is a pulsating DC type, that is similar to that of a full wave rectifier. Although the maximum, the peak value is 5 volt. So now the next thing is we need to calculate what is the DC voltage. So if the waveform is full wave, so the DC voltage or the average voltage can be given as 2 Vm by pi. So 2 Vm by pi, we can use this, we can multiply this 5 multiplied by 0.636 and we are getting a result which is VDC equals to 3.18 voltage. So till date we have seen the rectifier circuit, both half wave and full wave rectifiers. We have not included any kind of let's say any kind of filter circuit, the capacitive filter or the inductive filter or the RC filter. If we include these type of circuits, so we can basically improve, we can basically smooth the output waveform. If we use a capacitive filter, the output waveform will not be like this, it will be something like this. We are getting a smooth waveform. So these rectifiers are generally used in the power supplies. So after this rectifier, since again it is not a pure form of DC what we are getting, so we need to use a IC which basically convert this pulsating DC into the pure DC form. So these ICs will be known as regulator ICs. Regulator ICs, we have several regulators available. Some of these regulators are Zener diode as voltage regulator, BJT as a regulator in a series configuration or in a shunt configuration. So this is all about the rectifier circuits. These are the references which I've used. Thank you.